So this is Lab 2, Charge Tape Revisited. So the purpose of this lab is to model the charge tape experiment from last week as a set of line charges rather than 2-point charges. And using this model, we're going to approximate the amount of charge necessary to float one tape above the other. And then we're going to compare the results from this model to the results from the point charge model. And the main result from this lab was that the amount of charge on one piece of tape is 5.80145 times 10 to the negative 8th coulombs. So the first concept that's important for this lab is the electric field of a point charge, which is pretty basic. Just K is the electric constant, Q is the charge of the point of the electric field you're trying to find, and R is the distance from the source of the field to the observation location. The second concept, which is new for this lab, is the electric field of a uniformly charged rod. And this is going to be used because we're treating the tape as a line of charges, or like a rod, rather than a point, which is more realistic. And in this equation, R is the distance from the center of the line to the observation location, L is the length of the line, and Q is the charge of the line, which is uniform throughout. And the final concept is electric force, which is force is equal to the external electric field times the charge at the observation location. So the assumptions that were made for this lab is that each U-tape had about the same amount of charge and is evenly distributed along the length of the line rather than at a point. That air resistance is ignored, and that the data from Lab 1 is applicable. So the length, mass, distance, gravitational force, we're going to use the same data. So the calculations I made for this lab is I use the electric field of a uniformly charged rod and use as the external electric field and multiply that by charge again. So that is what the right-hand side of this equation is, and that will be equal to gravitational force. And by plugging R in as 0.0508, which is the distance between the two tapes, and L as 0.3175, which was the length of the tape, we could solve for Q, which was 5.41049 times 10 to the negative 8th. And as you can see, the actual number was 5.80145 times 10 to the negative 8th, but I'll explain that later. So for the actual computer model, the constants were the electric constant, gravity, distance, and the length of the tape, the mass of the tape, and also the actual Q, which was this value down here. And to find that value, I started with the value I initially calculated and then used trial and error to find a Q value that would result in an electric force equal to the gravitational force, which ended up being 5.80145 times 10 to the negative 8th. And here you can see the electric field function, which is E field, and the line charge function, which is line charge. And this would calculate the electric field for each point, and the line charge function creates the line charge. And at the top of the top two lines of this image, it creates the line charge visually. So top tape creates the line charge of the top tape, bottom tape creates the line charge of the bottom tape. And all this code right here, this is calculating the individual electric fields at each individual point, which is modeled by a green arrow, and then it adds all those together into a total electric field and then uses that to find total electric force. And here, this is where we're creating the force arrows. So first, it finds the midpoint between the arrows, and then it puts an arrow modeling the electric force and an arrow modeling the gravitational force at that point. And here's the result. So the system here is the top tape, which is the red spheres, and the surroundings is the blue spheres, or the bottom tape. And the yellow arrow is the gravitational force, gray is electric force, and all these green arrows are the individual electric fields at each of these individual spheres. So some sources of error in this lab is that the charge may not have been uniformly distributed across the tape, which we assumed it would be. The data measured in Lab 1 could be inaccurate, or there could be some rounding errors by the computer. And for the discussion questions, comparing the line charge to the point charge, the line charge is much greater than the value from the point charge by a factor of 1.94. And these estimates differ because one, we're putting all the charge at a single point, while the other is distributed across a line, where the line charge, it will consider the length of the line, while the point charge does not. And the line charge value is more likely to be closer to the real value because the tape is more like a rod-like structure or like a line, with charges distributed along the length of it rather than a single point. And in conclusion, representing the experiment as a set of line charges leads to a greater charge that is more accurate, and it works by adding all the individual electric fields on the top table, which are those little spheres.